Chapter 5.3, Inverse Functions. Day 1, Properties of Inverse Functions and Finding Inverse Functions. This is a quick review from pre-calculus. We're going to look at what does it mean to be an inverse function, a little bit of calc topic to it, and then finding inverse functions. Right? So first off, the definition of inverse functions. Inverse, in one word, means opposite. Right? The inverse is an opposite of a function. So for example, if we got the ordered pairings of 1, 4, 2, 5, 3, 6, 4, 7, which comes from the function x plus 3, the opposite of that would be if we took 4, 1, 5, 2, 6, 3, and 7, 4. So we just switch them around. And that instead of being x plus 3, we did x minus 3. Inverse means opposite. A couple things you want to notice about the opposite function or the inverse function is that your domain and range are switched. 1, 4 switched to 4, 1. 2, 5 switched to 5, 2, and so on. Because they're opposites, they have the effect of undoing each other. Okay? They undo each other. They're opposites. So whatever you do to x ends up being undone by the inverse. So when we take the function and compose it with its inverse, or the inverse and compose it with its function, we end up going back to x. And that's what brings us to the definition of the inverse. If you take a function and compose it with another function, and you get back down to x, you have found that they are inverses. All right? So for every value in g, if you can get it back to x when you compose it into f, and for every value of x in the domain of f, you can compose it in g, you get back to the inverse. Let's do that. Let's verify that these two functions are inverses. So we need to do two things. All right? We need to do f of g of x, and we need to do g of f of x. All right? We'll take g and put it into f. G is the cube root of x plus 1 over 2. All right, we'll put that into x. So 2 times the cube root of x plus 1 over 2 minus 1. And we'll simplify that. Oops, I forgot my cubed here. All right, we'll simplify that. First off, the cube and the cube root, they cancel straight up. So we got 2 times x plus 1 over 2 minus 1. We will continue. The 2 here and the 2 there will cancel. We got x plus 1 minus x. So that one composes down to x. If we try that with g of f of x, where we take f, which is 2x cubed minus 1, and throw it into g. So we got the cube root of 2x cubed minus 1 plus 1 over 2. And simplify. We can get rid of the parentheses here. So we got 2x cubed minus 1 plus 1. Well, minus 1 plus 1, those are opposites. So those will cancel. We got the cube root of 2x cubed over 2. Again, 2 over 2 reduces. We got the cube root of x cubed. So we got x. All right? Since they both reduced down to x, they are inverses of each other. So we can say that g of x equals the inverse of x. Or vice versa, f of x equals the inverse of g of x. When you can compose them both ways down to x they are inverses. And I say both ways because an example of a function that works one way but not the other, f of x equals x squared, g of x equals the square root of x. All right. If I take g of f of x, I take f and throw it into g, I get that. If I take g, and throw it into x, f, I get this. All right. If I simplify this down, or actually let's start with this one. If I simplify this down, I get x. Every g will simplify down to x. Or every x and g will simplify down to x. But if I simplify this down, every x in f, that will simplify down to the absolute value. Because first you're squaring it to get a positive number, then you go backwards. But the square root, you take the principal square root, you get the positive square root of x. So here's an example where it doesn't work. That's why you must check both of them. All right, moving on. And we just kind of talked about this reflective property. They switch. Their domain and range switch. So the point A, B, and F, you switch it, it becomes the point B, A in the inverse. That's just because inverse means opposite. All right. Now, this is very important. Every function has an inverse. However, not every function has an inverse function. What do I mean? Well, here's a parabola. That has an inverse. Inverse means opposite. You take the opposite, it looks like that. By the way, the opposite is also a reflection over the line y equals x, because that's where x and y switch. Right? Notice the opposite is not a function because it does not pass the vertical line test, which would imply a horizontal line test to see if there is an inverse function. All right? Another way we can say that is it's one-to-one. Right? One-to-one means it passes the vertical line test to be a function and a horizontal line test so that the inverse has a function. It's one-to-one. Every x has one y. Every y has one x. All right? So you got to have something that's like this, where it doesn't double back on itself, up and down, or left and right. All right? An example of a non-function, again, or not a function that does not have an inverse, again, is a parabola. It's not one-to-one. It doubles back. And another thing we say is it's strictly monotonic, meaning it's always going up. It doesn't come back and go down. That would create this. Or it's always going down. Monotonic means it's always going up or always going down. So if we take a look at our next problem, verify which of these functions has an inverse function. Well, we can't find the inverse function of these. It's kind of hard. It's a cubic. But we can show that it's monotonic, meaning it's always increasing or always decreasing, always going up or always going down. And we do that, increasing, decreasing, with the first derivative. So if we take a look at A and find the derivative is 3x squared plus 1. Now, critical numbers of this derivative, there are none, because you can't square a number, add 1, and get 0. So this one is always positive. So the derivative is always positive, so it's monotonic. So f inverse exists because the derivative is always positive. If we took a look at B and found our derivative there, we can see that there's a critical number at the square root of 1/3. And if we plot a number line there, At 0, it's negative. At 2, it's positive. And you can see that it changes from decreasing to increasing at the square root of 1/3. It's not monotonic, so the inverse does not exist. Okay? Because it is not always increasing or always decreasing. All right? So often it's easier to prove whether it has an inverse than to actually find the inverse. So we're going to be looking at first verifying an inverse sometimes before we look for it, or we can do stuff with it once we know it has an inverse. All right? So just as the last example, how do you find an inverse when it's easy to find an inverse? Well, use the definition. Inverse means opposite. So instead of writing f of x, which we know stands for y, we'll write the opposite. X equals the square root of 2y minus 3, and solve for y. Undo the square root by squaring. Undo adding 3 by subtracting. Or undo subtracting by adding, and then divide by 2. So the inverse function is x squared plus 3 over 2. However, remember that this is a parabola, so there's some restrictions. We need to look at the range here, and that becomes our domain here. So on this problem, 2x, square root of 2x minus 3, it ends up shifting because we subtract 3, and actually we subtract 3 halves with a stretch. We're shifting to the right 3 halves. So this domain, x, is greater than or equal to 3 halves. There's our inverse. All right, so in review, inverse means opposite. You can verify if there is an inverse without actually finding the inverse by seeing if the derivative is always positive or negative. That means monotonic. If there is an inverse, f of f inverse of x equals x, as does f inverse of f of x. And to find the inverse, you're going to switch x and y, solve for y.